Hey guys, Mr. Betts here. I'd like to talk a little bit about infinite series and convergence and divergence in regards to infinite series. Convergence and divergence should be ideas that we're familiar with from doing limits. Infinite series, it's best to talk about those just by looking at some examples. So this is an infinite series. So an infinite series is basically just a sum that is infinite. So we have infinitely many terms, and we want to look at that sum. So if you remember when we have the sigma notation, essentially what we're going to do is we're going to take, starting at this value here, we're going to take numbers and plug them in for n, and we're just going to count up from there, from 1. So we plug 1 in for n and we get 2. We plug 2 in for n, we get 2 squared, which is 4. We plug 3 in for n, we get 2 cubed, which is 8. Plug in 4, we get 16, 32, and so on. So it hopefully is kind of obvious to you that if we start adding up the terms in the series, the sum is going to get really big really fast. And since we have infinitely many terms and the terms are getting bigger, then this sum is going to get really big. So this sum is going to be divergent. So this is going to be a divergent infinite series. The question is it possible for an infinite series, so a series with infinitely many terms, to converge? So to answer that question, I want to look at this series here. So it's really similar, except instead of the terms getting bigger, now they're going to be getting smaller. So if we plug 1 in for n, we get 1/2. If we plug 2 in for n, we get 1/4, then 1/8, 1/16. So we're still going to have infinitely many terms that we're adding together, but now the terms aren't getting really big, so the sum isn't growing very fast. So the question is, if we were actually able to add all of these infinitely many terms together, could we still get a finite sum? And I want to try to answer that question by looking at what happens just as we go through that process. So if we start adding some terms together, just looking at the first term, we're starting at 1/2. Then we add on the 1/4 and we get 3/4. Then we add on the 1/8 and we're going to get, what would that be? 7/8. Then we add on the 1/16 and we're going to get 15/16. Then we're going to add on the 1/32 and we're going to get 31/32. And there's a pattern here that hopefully you recognize. Essentially what's happening is the denominator is doubling each time, and the numerator is always 1 less than the denominator. So even though these terms are getting bigger, if we were to plot these numbers on a coordinate plane, when n equals 1, we had a sum of 1/2. So if this is 1, when n equals 1, our sum was 1/2. When n was 2, our sum was 3/4. When n is 3, our sum was 7/8. And we're going to be getting a sum that's getting closer and closer and closer to 1, but never actually get to 1. So even though we're adding infinitely many terms together, the sum is actually bounded. And if we add all these terms together, it's going to be 1. So it's kind of a weird idea that we can add infinitely many terms together and still get a finite value, but that is in fact what's happening here. So let's look at this a little bit more formally. If we want to define a convergent series, the first thing we need to do is define what's called a partial sum. So I used the idea of partial sums in this last example here. These sums that I got as I added more and more terms together, those are what are called partial sums. And a partial sum is exactly what it sounds like. It's a sum of a part of a list. So we define the nth partial sum as the sum of the first n terms of a series, and it's denoted s sub n. So this is a subscript, so we read that sub. So looking at this series right here, the first partial sum is just the first term. That's s sub 1. The second partial sum is s sub 2. The third partial sum is s sub 3. The fourth partial sum is s sub 4, and so on. So the nth partial sum is s sub n. Now, using this idea of partial sums, we can define what it means for a series to be convergent. So if we want to know if this series converges, what we did is we said, okay, what happens as we get more or deeper and deeper into these partial sums? And those partial sums are actually approaching a value of 1. So they're approaching a value. So this is getting into the idea of a limit. So in order to define a convergent series, we're going to look at a limit. So I want to look at this series again here. So this is going to be 1/2 plus 1/4 plus 1/8 plus 1/16, and I'm going to look at the partial sums here. So the first partial sum is 1/2. The second partial sum is 3/4. The third partial sum is 7/8. And I'm going to do one more here. And I'm going to look at these partial sums. I'm going to write them in a little bit of a different way so that we can look at this in terms of a limit. So I mentioned this already, but each numerator is 1 less than the denominator, and each denominator is 2 to the nth power. So we're going to get 2 to the first power on the bottom, and this is 2 to the first minus 1. Then we get 2 to the second power on the bottom here, and it's 2 squared minus 1 there. So 2 squared is 4, minus 1 is 3, and that pattern is going to continue. So we have 8 minus 1 over 8. Then we're going to have 16 minus 1 over 16. And the reason I did that then is because I can generalize the nth partial sum using that pattern, and it's going to be 2 to the nth power minus 1 over 2 to the n. Or a more useful way of writing that is going to be 2 to the n over 2 to the n is 1 minus 1 over 2 to the n. And this is useful because we can see then as the partial sums get really big, if we plug a really big number in here for n, we're going to have 1 minus 1 divided by a really big number. 1 divided by a really big number is a really small number, so these partial sums are approaching 1. So formalizing that, we're going to use a limit that looks like this. So that limit is what we're going to use, and we're going to say an infinite series converges to a number s. So we say the sum is s if and only if. That might be something you remember from geometry, biconditionals. So if and only if the limit of its sequence of partial sums exists and equals s. So if this limit exists, then the value that we get for that limit is going to be what the series converges to. So the partial sums here, I said, was going to be 1 minus 1 over 2 to the n. This is not something that I would expect you to do for series in general, but it works out for this series, so we can use it to look at this. So that means that this sum here is going to equal the limit as n approaches infinity of s sub n, which is going to be 1 minus 1 over 2 to the n. And as n gets really big, 2 to the n gets really big. So this approaches infinity, which means that this term approaches 0, and that limit is 1. So since that limit exists and is 1, the sum of this infinite series is going to be 1.